Hello, everyone. My name is Richard Ren. I'm a PhD candidate at Carnegie Mellon University. Thanks for your interest. Today, I'm going to present my work, Loosely Synchronized Search for Multi-Agent Pathfinding with Asynchronous Actions. This work was in collaboration with Professor Sivakumar Rathinam from Texas A&M University and Professor Howie Choset from Carnegie Mellon University. So multi-agent pathfinding, MAPF, has been extensively studied and applied in many applications such as logistics and surveillance. The basic version of the MAPF problem can be described as follows. Let the index set I represent a set of n agents. All agents move in a shared workspace, which is represented as a graph G with vertex set V and edge set E. Each agent has its respective initial vertex and destination vertex. An individual path of agent I is a sequence of vertices connecting any two vertices in the graph. There are two types of conflicts along a joint path. A vertex conflict means a pair of robots occupies the same vertex at the same time. An edge conflict, or say swap conflict, means a pair of agents that are moving through the same edge from the opposite directions at the same time. Each edge within the graph has a non-negative cost value. The goal of this problem is to find a set of collision-free paths for all agents from their respective start to destinations while the sum of path cost reaches the minimum. Okay, in this problem, we introduce a duration function di for each agent that maps an edge to the amount of time for agent I to go through this edge. Note that here, for the same edge, different agents can have different durations. And for the same agent, different edges can be mapped to different durations. This duration function describes the asynchronous actions among agents as there is no common unit time action among all agents now. In conventional MAPF, duration is always a common constant for all agents and all edges. Along with the duration function, first we define an agent to occupy both ends of an edge during the transition through the edge. If any two agents occupy the same vertex at the same time instant, we say there is a conflict. Second, the cost of an edge is the same as the duration of an edge. In other words, this work aims to minimize the sum of arrival time. It's also worthwhile to point out that waiting place actions can be described as a self-loop in the graph, and the above definition of duration and conflict still applies. Okay, there are several related work in the literature. In recent years, many variants of MAPF have been studied. These variants span a spectrum from the basic MAPF to multi-agent motion planning, MAMP. Along the spectrum, different variants trade off between the generality of the problem formulation and the computational efficiency of the algorithm. A highly similar MAPF variant to this problem is the MAPF with continuous time, where an algorithm called continuous time CBS, or CCBS for short, has been proposed to solve the problem. In this work, we use CCBS as a baseline. This work focuses on A*-based MAPF planners. It is known that there is no single MAPF planner that outperforms all others in all settings. As far as we know, no A*-based MAPF planners have been extended to handle asynchronous actions. We developed a method called Loosely Synchronized Search, LSS, that can potentially be applicable to all A*-based methods. To verify this idea, we implement LS-A*, LS-M*, and we also fuse LS-M* with CCBS under the framework of meta-agent conflict-based search, MACBS, to achieve the state-of-the-art performance. Okay, so far we have covered problem definition, motivation, related work, and the rest of this presentation includes methods, results, and conclusion. So a technical challenge to extend A*-based multi-agent planner to asynchronous actions is that there is no such a concept about a common time cycle for planning. In conventional MAPF, intuitively speaking, all agents always start or stop their actions concurrently, and the planner can always identify a common time cycle, or say plan steps, so that the planner can compute step by step. A naive approach to handle this challenge is to find a common unit time among all agents' actions and then discretize the time axis into unit time steps. Then A star can be used to search over the entire time axis. However, as one can expect, this naive solution is very inefficient as it may require a too fine discretization of the time axis. Now let's go through the idea of loosely synchronized search, LSS, via a toy example. We define a search state to be a set of individual state Si for each agent I. And an individual state Si is a tuple of parent vertex, current vertex, the arrival time at the parent vertex, TPSI, and the arrival time at the current vertex, TSI. These times are also called timestamp. For the parent vertex, it is called the timestamp of the parent vertex, and for the current vertex, it's the timestamp of the current vertex, or timestamp for simplicity. In this toy example, we have two agents locating at vertex F and E respectively. The duration for the red robot and the blue robot to go through each edge in the graph is set to a constant number 1 and 3 respectively. The initial individual state for the red robot is FF00, which means the robot moves from F to F between time 0 and 0. And the initial state for the blue robot is EE00. Now to expand a state, LSS first computes the minimum current timestamps of all agents. In this toy example, Tmin is the minimum value of the two values in red, which is 0. Second, LSS finds the subset of agents that have their current timestamps equals Tmin, which is denoted as Itmin. In this example, Itmin includes both agents. Intuitively, Itmin includes all the agents that are supposed to move because they have the minimum timestamp. Okay, then possible actions for each agent in Itmin is considered, and all possible successor states are generated. In this toy example, there are 4 successors. Agent 1 can move or wait, and agent 2 can either move or wait. And by taking the combination, there are 4 possible states. Among them, for the first state, both agents wait in place, which clearly cannot lead to an optimal solution. And here we introduce a dominance-based pruning rule, which compares the timestamps of 2 states that have the same current vertices. More details about this dominance pruning rule can be found in our paper. Among those 4 successor states, the last one clearly leads to conflicts as both agents occupy vertex B between time 0 and 1. It is therefore pruned. Then for all remaining successor states, they are inserted into open based on their F values, just in the same way as A-star searches. Ties are breaking at random. In this example, for the second round of the expansion, let's say the state FF01, EB03 is selected from open for expansion. And this time the Tmin value is 1, which is a minimum of 1 and 3, and correspondingly Itmin contains robot 1 only. To expand, only the possible actions of agent 1 is considered and the individual state of agent 2 remains the same. In this case, when agent 1 moves, it runs into conflict with agent 2 and the corresponding successor state is thus pruned. When agent 1 waits, LSS will find the second minimum timestamps among all agents and lets the robot wait until then. As we can see in this example, the individual state of agent 1 now becomes FF13. Here 3 equals the second minimum timestamp. Okay, now let's stop with this toy example and summarize the key points and the intuition behind. So first, a new type of search state is introduced to capture the time information of agents. And second, to expand the state, we introduce concepts like Tmin, Itmin to decide the subset of agents that should be considered for their next moves. In addition, the waiting time is determined by LSS by letting robots wait until the second minimum timestamp in that state. The intuition is that between the minimum and the second minimum timestamps, the vertices occupied by all agents do not change, and there is no need to consider the timestamp in between. Third, a dominance-based pruning rule is introduced to remove states that cannot lead to an optimal solution. With all that in hand, in our paper, we show that LSS is complete and computes an optimal solution. To verify LSS, our first task is to compare LSS with a naive A-star method. Here, naive A-star assumes the existence of a common time unit tau and a maximum possible time t, and then discretize the time dimension into a finite number of time steps. This discretization guarantees that the actions of all agents begin or end concurrently. Naive A-star conducts A-star search in a time-augmented graph by visiting all possible time steps. In this test, we use an obstacle-free map of size 16 by 16. We fix the number of agents to 2, and we let the duration of each agent over all edges be a constant integer randomly sampled from 1 to k, where k equals 10, 100, or 1,000. As we can see from the table, LSA star, as expected, clearly outperforms naive A star, as naive A star requires a true fine discretization of the time axis, while LSA star does not. Okay, next, we implement LS recursive M star, continuous time CBS, and embed them into the framework of meta-agent conflict-based search. By tuning the hyperparameter B, the merging threshold, MACBS varies its behavior from LS recursive M star to continuous time CBS, or something hybrid in the middle. In this test, we select 3 different maps and test with different number of agents. We set a runtime limit of 5 minutes and measure the success rates and the average runtime over all instances. It turns out that in many settings, the most efficient algorithms lies in the middle of the spectrum, which is some hybrid of LS recursive M star and CCBS. The result also shows that there is no single MAPF planner that outperforms all others for MAPF with asynchronous actions. Okay, after that, we introduced the inflated heuristics and evaluated bounded suboptimal LS M star and LS recursive M star. Clearly, by increasing the inflation rate W from 1.0 to 1.5, LS recursive M star achieves higher success rates and shorter runtime in all settings. Finally, we verify the approach with Robotarium, a remotely accessible multi-robot testbed. As you can see in the video, in the middle, we have the planar view, a graph, and on the left, we have the simulated motion of the robot, and to the right, we have real robot motions. Okay, to conclude, in this work, we formulate the problem called multi-agent pathfinding with asynchronous actions. To solve it, we propose a method called loosely synchronized search, LSS. We implemented LSS as LS A star, LS M star, LS recursive M star, and eventually we embed them into the meta-agent conflict-based search framework. We run massive tests to verify the performance. In terms of future work, one can consider extending LSS to other A-star-based planners, such as EPE A-star. One can also consider further generalized LSS to other MAPF variants, such as multi-agent motion planning. Okay, that's the end of the talk, and thank you for listening.